Okay, so today's lesson is testing for functional groups, and this is the AQA specification, and we're looking at organic chemistry here. Okay, so I want to start off talking about which functional groups we're going to be testing for. So we could be testing for alcohols, and there are several different types of alcohols. We've got primary alcohols, secondary alcohols, and tertiary alcohols. We might also be testing for aldehydes and ketones. So we could be looking at an aldehyde like this. There's our functional group for an aldehyde, and our ketone, as you can see, the carbonyl, the C double bond O, is in the middle of the chain. Finally, we could be testing for a carboxylic acid. So you can see you've got C double bond O, OH group here, or we could be testing for alkenes, the CC double bond there. So your first task, I want you to pause this video, and on your worksheet you should find a table with all of these compounds in. And for each one, I want you to give me the International Union of Pure and Applied Chemistry name, then construct a structural formula for each, and then draw skeletal formulae for each. So if you pause this video, go over to your worksheet and fill that in, and then come back to the video and have a look for the answers, and you can check yours. Okay, right then. So our answers should be as follows. So this compound here is 1 long, so that gives us the prefix meth, okay, or meth, and it's got an OH group bonded to the carbon, so it's methanol. We don't need to number the carbon here because there is only 1 carbon. The structural formula for this, well, we've got a CH3 and an OH, so we're going to go for CH3OH. And the skeletal formula, well, we've got 1 carbon, shown by the terminus of the bond here, and then that's bonded directly to an OH group. Okay, over here it's 3 long, which gives us the prefix prop, and the OH group for the alcohol is on the 2nd carbon, so we're going to call this propan-2-ol. And the structural formula for this, well, we've got a CH3, a CH, an OH coming off of the main chain, so we're going to bracket that, and then a CH3. CH3, CH, OH, CH3. Now for the skeletal formulae, you needed CH3, CH, CH3, and there's your OH coming off the side. Okay, let's have a look at our next one then. So we've got 3 carbons is our longest chain here, but coming off of that longest chain, we've got a methyl group, and it's still a propan-2-ol because the OH group is coming off of that 2nd carbon. So we should have a 2-methyl propan-2-ol here. Now, as for the structural formula, we need to show that this is coming off of the side chain, so this bit's going to need bracketing up as well. So we needed CH3, which is that bit there, C, which is this carbon here with no hydrogens, OH coming off of the main chain, CH3 coming off of the main chain, and then our CH3 on the end here. And we're going to draw that skeletally like this. CH3, 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 there's the C, and there's the OH on it. Moving on. Right, next up we've got this compound here, looks to be an aldehyde based on the carbonyl, C double bond O, bonded straight to a hydrogen on the end of a chain, and it's 3 long in terms of its number of carbons, so we've got propanol. Okay, structural formula CH3, CH2, CHO, chocho aldehyde there, and the skeletal formula looks like this. There's the CH3, there's the CH2, there's the CH, don't bother showing the H, and the double bond to the oxygen. Next up, we've got a carbonyl in the middle of a chain, not on the end, so we're looking at a ketone here, and because it's 3 long, it's propanone. No need to number where the ketone is in this particular example because there is only 1 possible position for a ketone with propanone. Obviously, if we're getting any larger than pentanone or larger, then we need to number it. Again, you wouldn't need to number it for butanone because there's only 1 available position there. Structural formula CH3, CO, CH3. No need to put that O in brackets there because that's really the only way it would bond with that number of atoms of each element. Structural formula, skeletal formula looks a bit like this. Okay, that's often known as acetone, by the way. There's your CH3, there's your carbonyl, and there's your other CH3. Okay, moving on. Looking at this, this appears to be a carboxylic acid, so it's going to be something oic acid. It's 3 long, so this one's going to be propanoic acid. Okay, CH3, CH2, COOH. There we are. Okay, and skeletal should look like that. Okay, we do show the hydrogens if they're bonded to heteroatoms, hetero meaning not carbon. Okay, so because this one's bonded to an oxygen, we can represent the hydrogen there. Okay, final one then. This appears to be an alkene, so it's going to be something ene. It's going to be just propene. There's only 1 available position for the CC double bond, so we don't need to number it with propene. Structural formula, there's 2 ways of doing these. We've got a CH2, CH, CH3, that's fine, but sometimes in the structural formula you will see the double bond shown, okay? But you don't need to do that. Both of these representations are correct, and here's your skeletal formula. Okay, so you can check that against your own work and make any corrections that you need to make. Right, so we're going to look at the oxidation of primary alcohols to start with. So the first thing to note is that our oxidizing agent for any alcohol is always acidified potassium dichromate. Potassium dichromate has the formula K2Cr2O7, but it's always acidified with sulfuric acid, H2SO4. So when you're writing the formula for this, just always write H2SO4/K2Cr2O7. Okay, this is our oxidizing agent, and if it works, if it succeeds in oxidizing an alcohol, then it's going to change from orange to green. That's how we know it's worked. So just a quick recap, your primary alcohols, if you oxidize them and then immediately distill that product of oxidation, then we're going to produce an aldehyde and water as a byproduct. If we carried on oxidizing that aldehyde, then that aldehyde would oxidize into a carboxylic acid. Bear in mind we'd need 2 moles of the oxidizing agent to get from the start all the way to the finish, to the carboxylic acid, but we could stop the reaction here at the aldehyde by using distillation. But if we want to go all the way, then you'll get the carboxylic acid, 2 moles of oxidizing agent. You would get, if you went all the way, you would get water as a byproduct here, but remember, just plain old the aldehyde to the carboxylic acid doesn't give you water. It's only this first step that actually gives you water. But obviously if you went all the way, then you'd already have that water as a byproduct as well. Okay, so here's an example of that, primary alcohol like methanol. That would oxidize into methanal, and that would produce methanoic acid, which is sometimes known as formic acid, the same sort of acid that ants produce. Okay, so that is our oxidation of primary alcohols, and remember this will always be accompanied by a colour change of orange to green with the acidified potassium dichromate. So this is your first task. Here are the questions. So your first question is name the oxidizing agent used on alcohols. Your second is give the formula for the oxidizing agent used on alcohols. Third question is state the colour change observed with this oxidizing agent. Fourth question is if you do want to obtain the aldehyde, how must you carry out the process? Next question is if you want to go straight to the carboxylic acid, how much you carry out the process? I think I'm supposed to say how should you carry out the process? And then an advanced question, can you explain the colour change of the oxidizing agent using half equations by referring to the oxidation states of chromium? If you pause the video here and then go over to your Google Doc, answer the questions, then come and compare back with these answers that I'm going to give to the video. Okay then, right. So our oxidizing agent, you should have named it as acidified potassium dichromate. As for its formula, you should have given us this, H2SO4/K2Cr2O7. You could have just written 2H plus here instead if you wanted to. The colour change should have been orange to green. To get the aldehyde, we've got to distill it, otherwise it will further oxidise into the carboxylic acid. If you want to go all the way to the carboxylic acid, you're going to use reflux. Now, the colour change of the oxidising agent. Well, chromium in acidified potassium dichromate is in the 6+ oxidation state. Because it's an oxidising agent, the way it actually oxidises something else is by accepting its electrons. So it takes those electrons away from something else. So oxidising agents actually oxidise another substance by themselves becoming reduced. So I've shown here the orange chromium 6+ ions gaining 3 electrons to become green chromium 3+ ions. Okay, so we could argue that chromium in the 6+ oxidation state is orange, and when it's reduced, it gains 3 electrons to form +3 chromium ions, which are green. Okay, next up, let's have a look at oxidation of secondary alcohols. Okay, so again, we're going to be using acidified potassium dichromate for this. Okay, so that's H2SO4/K2Cr2O7. You have to remember those formulae. And again, they will change from orange to green when successfully oxidizing the secondary alcohols. The thing to note though is that a secondary alcohol just plain old oxidizes straight into a ketone and water. Okay, so an example here, if I took propan-2-ol that you named at the start, that would oxidize into propanone. Okay, so that's all that happens, you get a ketone with those. Looking at oxidation of tertiary alcohols though, if we tried to use acidified potassium dichromate to oxidize tertiary alcohols, then you would actually get no reaction whatsoever. And there's a reason for this. If we looked at what a hypothetical product would be, i.e. double bonding that oxygen there, which has happened in all of these oxidations so far, then this carbon would actually end up what we call pentavalent. That would mean it's got 5 bonds. And you can see that my ChemDraw program's come up with this little red box around it to say that that's an error. You're not going to have that. You're not going to have a carbon that has 5 bonds. Okay. The only way to fix that would be to break off one of these groups here of carbons And actually dichromate is not a strong enough oxidizing agent to break a CC single bond. So that's not going to work. Okay, so you're not going to be able to oxidize a tertiary alcohol. But what does that mean for our observations? Well, it means that your acidified potassium dichromate is not going to change from orange to green. It's actually just going to stay orange. Okay, so the acidified potassium dichromate will not change color. All alcohols can be oxidized though by burning them. Okay, so if you were asked what is a suitable way of oxidizing a tertiary alcohol, well, you could say try to combust it completely in oxygen. That would oxidize it, and that would break the carbon-carbon bonds. But acidified potassium dichromate is not going to carry out this oxidation reaction. Okay, so your next task, I want you to tell me what secondary alcohols oxidize into. Write a structural formula equation for the oxidation of butan-2-ol into butanone. Tell me what colour change you would get when 2-methyl-butan-2-ol is oxidised with acidified potassium dichromate, and explain that colour change. Okay, so if you could pause the video here, I gave one of them away then, and answer those questions on your Google Doc, and then come back to the video and check and improve your answers. Okay, so secondary alcohols oxidise into ketones, you should have got for that first one. Here's your structural formula equation for the oxidation of butan-2-ol into butanone. Okay, so there's our structural formula for butan-2-ol, plus an oxidizing agent is going to make a butanone and water. We're only carrying out one oxidation, so we only need one oxidizing agent featuring in the equation there. You may have chosen to write reflux above the reaction equation to maximize the yield of that chemical reaction. Okay, bear in mind water is your byproduct there. Okay. Next up, we're going to get a colour change with 2-methyl-butan-2-ol. Right, if you actually drew out 2-methyl-butan-2-ol, you should have noticed that that was a tertiary alcohol. This was a trick question. So you're going to get the acidified potassium dichromate remaining orange, okay, and it's going to remain orange because it's a tertiary alcohol and it cannot be oxidised by the potassium dichromate because we're looking at a tertiary alcohol there. Okay. So how do we actually use these tests now to test for alcohols? Well, we need to be able to explain this method, okay? So we're talking about how we could distinguish between primary, secondary and tertiary alcohols. So if you take a test tube and fill it with 2 centimetres cubed of acidified potassium dichromate, you probably want to use a glass pipette to transfer that into there, okay? And then if you take about 10 drops of whatever alcohol you're looking at, and that alcohol, again, you don't know whether it's primary, secondary or tertiary, and if you drop that into the test tube containing acidified potassium dichromate, then heat it up in a water bath. Okay, so you're going to use a water bath, a hot water bath, to warm that mixture gently. It's important that you warm it gently. Now, here are your potential outcomes. If that orange acidified potassium dichromate slowly turns green, okay, then you must have either a primary alcohol or a secondary alcohol, okay? If it stays orange instead, then you're looking at a tertiary alcohol. So hopefully now some of you have noticed the problem with this test. This test does not differentiate between primary and secondary alcohols. They both give the same result. So we need a follow-up test that enables us to distinguish between the primary and secondary alcohols, and I have the answer for that. The answer is this. Well, when we oxidise a primary alcohol, it turns into an aldehyde. When we oxidise a secondary alcohol, it turns into a ketone. So what we're actually going to do is test the products of oxidation. We're going to try and distinguish between the aldehyde and the ketone, because both of these in their initial oxidations give the same result, orange to green with acidified potassium dichromate. So the main way we're able to distinguish between the aldehyde and the ketone is the idea that an aldehyde can be oxidised further, whereas a ketone can't be oxidised further. So if we use an oxidizing agent to try to distinguish between the aldehyde and the ketone, this one will oxidise, this one won't. But we're not going to use the same oxidizing agent again. We're going to use an oxidizing agent that's specifically targeted for aldehydes. Okay, and the answers for that are Tollens reagent, that's an oxidizing agent specifically for aldehydes, or Felling's solution. Okay, so these two will enable us to distinguish between an aldehyde and a ketone on the basis that only an aldehyde can be oxidized further. Okay, so let's have a look at Tollens reagent. So if you're describing how you use Tollens reagent, you always have to say I'm going to warm it up with Tollens reagent. And remember that Tollens reagent itself is an oxidizing agent. Okay, Tollens reagent, a few details for you. It's ammoniacal silver nitrate. That means silver nitrate dissolved in ammonia. It forms this thing called a complex ion. You've got a silver plus ion there, so silver 1 plus ion, with two what we call ligands of ammonia, neutral ligands. And the charge of that silver shines through in the overall charge there of the complex ion. Okay, so that's a source of aqueous silver plus ions. Now, our aldehyde that was produced from the oxidation of a primary alcohol is oxidized by the Tollens reagent. Okay, so the Tollens reagent oxidizes the aldehyde into a carboxylic acid, and in doing so, it forms a silver mirror precipitate. Whereas our ketone, if you tried to oxidize it, it wouldn't work. You can't oxidize a ketone further. Remember, that ketone would have come from a secondary alcohol. Okay, so these are the products of oxidation, the aldehyde and the ketone, only one of which, the aldehyde, can be oxidized via the Tollens reagent into the carboxylic acid. And our Tollens reagent is going to give a change that tells us it's oxidized an aldehyde. Okay, so remember that an oxidizing agent is something that oxidizes another substance. It removes electrons from another substance by itself being reduced. It gains electrons. And because our Tollens reagent is a source of silver plus ions, silver plus, it gains electrons itself and forms this silver solid, and that will come out as a precipitate. And our observation for this is that the aldehyde gives a silver mirror precipitate, whereas the ketone gives no reaction. So the silver mirror precipitate is this solid silver being formed from the aqueous silver plus ions when the oxidizing agent itself is reduced by gaining electrons. And that looks a little bit like this. You can see that the sides of the test tube, if you swirl the test tube as you're doing this, they develop this beautiful silver mirror precipitate around the outside, which is really stunning to look at, but the indicator that an aldehyde has been detected. Okay, let's have a look at our alternative now, the Fellings solution. Okay, again, we've got a warm with Fellings solution. This is another test for aldehydes and oxidizing agent. What is Fellings solution? Well, it's an alkaline solution of copper sulfate, and it contains copper 2 plus ions, which are blue. Again, if we looked at our products from oxidation of a primary versus a secondary alcohol, well, if we oxidized a primary alcohol, we'd get an aldehyde, which could be oxidized further by the Fellings solution into a carboxylic acid. Whereas our ketone, that is the product of oxidation from a secondary alcohol, could not be oxidized further. Okay, recap. Our oxidizing agent is a substance which oxidizes another substance by itself being reduced. Okay, so it gains electrons by removing electrons from the substance it's oxidizing. So the aldehyde is going to have electrons removed from it in the process of being oxidized. Okay, and as we said, our Fellings solution is a source of copper 2 plus aqueous ions, and then itself, as it's the oxidizing agent, it's getting reduced. So it's going to gain an electron to form copper 1 plus ions. Now, those copper 1 plus ions are actually in the form of copper 1 oxide, which has this formula here, Cu2O. Okay, and that comes out as a solid precipitate. So our observation here is that we have a blue solution, which then gives us this brick red precipitate of copper 1 oxide. Okay, it's good to mention that copper 1 oxide if you can. Remember to call it brick red and not just red. Now, the observation with the ketone, well, as it's never oxidized itself, it can't give the oxidizing agent, the Fellings solution, it can't give it any electrons. So no reduction of the oxidizing agent takes place, so there's no reaction, no change, so the solution will stay blue. Okay, and there's an example of what the Fellings solution will look like after it's oxidized an aldehyde and itself been reduced to form the brick red precipitate. Okay, let's have a look now how we could identify carboxylic acids, because it's important to remember that if you oxidize a primary alcohol, then yes, initially it makes an aldehyde, which you could distinguish from a ketone by using Tollens reagent or Fellings solution. But remember that they oxidize again into a carboxylic acid if we go all the way using reflux. So it might be that you actually want to identify this carboxylic acid instead. Okay. Now, the important thing to remember about carboxylic acids is that they are weak acids because they partially ionize, which means that they release H plus ions into solution. And any acid will undergo a neutralization reaction with a carbonate. Okay, so if we react an acid with a carbonate, it's going to start producing this carbon dioxide gas as well as water and a soluble salt. So here's a reaction equation for how an organic acid like ethanoic acid could react with something like sodium carbonate. Okay, so ethanoic acid plus sodium carbonate, there's the formula for aqueous sodium carbonate there, the test for acids, okay, is going to form sodium ethanoate, okay, because we used ethanoic acid. So whichever carboxylic acid you use, you get an anoate of that carboxylic acid. So just some wordplay here. Methanoic acid with sodium carbonate would give sodium methanoate. Ethanoic acid, sodium ethanoate. Propanoic acid, sodium propanoate. Okay, so whatever carbonate you've got the metal anoate of the carboxylic acid, or the metal carboxylate as it's sometimes known. Okay, that will give you also carbon dioxide and water. Structural formula equation here. The H of the carboxylic acid is replaced by a sodium ion. So there's sodium ethanoate. So this bit here is the ethanoate, and there's the sodium. Now to balance this for the number of sodiums in the sodium carbonate, each ethanoic acid picks up one sodium. Okay, so because this has two sodiums in it, we need two ethanoic acids in order to balance. We're going to make a mole of carbon dioxide and a mole of water here. Now this carbon dioxide is the key to this test, because I must insist this is the test for carboxylic acids. You add, why is it not working here? We add, there we go, aqueous sodium carbonate. The test for atoms is aqueous sodium carbonate solution, Na2CO3 aqueous. And this gives us effervescence of carbon dioxide gas. That's what you see, that's your observation. Now you might want to confirm that that's carbon dioxide gas and not say like hydrogen or another gas, sulfur dioxide, something like that. So what you could do is you could bubble this carbon dioxide gas through lime water, through a delivery tube into a test tube filled with lime water, and that would change from colourless to cloudy if the lime water had correctly detected carbon dioxide as the product there. So test for acids or carboxylic acids, aqueous sodium carbonate solution. You've got to say that all, don't just say sodium carbonate. Observation, effervescence of carbon dioxide gas, bubble through lime water, colourless to cloudy. Okay, so you've got the next task here. Now what I want you to imagine is I've got three alcohols, X, Y and Z. One of them's primary, one of them's secondary, one of them's tertiary. And what I've done is I've carried out an oxidation in the first step, and here's the results that were obtained via acidified potassium dichromate, warming them with it, okay, in the test tube. Then what I did was take the product of that oxidation, react it with toluenes, react it with Fellings, okay? And then what I did as well is I took that oxidation product of the initial oxidation of those alcohols and oxidized it again to see if it underwent a second oxidation. And then I tested that with aqueous sodium carbonate. So think about what that's the test for. Bubbled that gas through lime water. So you've got a few blanks here to fill in the results for, okay? It could be that you could expand these a little bit more as well. I've written no result, but if there's no result, what colour would it stay? Maybe you could change those as well. So try and add as much detail as you can to this table. Okay, pause the video here, then come back to it, and then we'll see what you've got. Okay, right then. Okay, so this one's changed from orange to green, which suggests we're looking at either a primary or a secondary alcohol here. But then again, it's given no result with toluenes. Okay, so if you've got something that gives no result with toluenes, then it's probably going to be a ketone. Okay, and ketones only come from secondary alcohols. So our first one, we should have got a secondary alcohol. Okay, next one's given no result with oxidation and no result with anything else. It's got to be a tertiary alcohol. This one's given a result of orange to green, so it might be primary or secondary. But then it's given a silver mirror precipitate, which suggests that it formed an aldehyde upon that first oxidation, which has been detected by the toluenes reagent. So we're looking probably here at a primary alcohol. So if it gives a positive result with toluenes, it'll also give a positive result with Fellings, because Fellings and toluenes are both tests for aldehydes. So we should be getting here a blue solution which gives us a brick red precipitate with Fellings. Okay. Then if I oxidise that aldehyde again, it would turn into a carboxylic acid. So the aqueous sodium carbonate should detect that carboxylic acid that's been formed, and therefore we're going to get effervescence of carbon dioxide gas, which we could then bubble through the lime water, which will turn from colourless to cloudy. Okay, so going back all the way to the start, the alcohol we managed to oxidise all the way up to a carboxylic acid must have been a primary alcohol. Okay, right, a few more questions for you. So I want you to have a look at these questions here, pause the video, and then come back to it, and we'll start to work through the answers. Okay, right, so a method for distinguishing between tertiary versus primary and secondary alcohols. So that's tertiary versus primary and secondary. Primary and secondary is one category there, okay? So let's start this off. So the first thing we're going to do is use a glass pipette to transfer 2 centimetres cubed of acidified potassium dichromate to a test tube. Then to that test tube, we're going to add 10 drops of the alcohol. We're then going to heat it gently in a hot water bath. And then if it changes from orange to green, then we've got a primary or secondary alcohol. And if it stays orange, then we're looking at a tertiary alcohol, because tertiary alcohols cannot be oxidised. Okay. Next, we've got 2 methods of distinguishing between aldehydes and ketones and giving the results. So the methods for distinguishing between aldehydes and ketones, really the test for aldehydes, which gives a null result with ketones. We have got warming with Tollens reagent. The positive result for an aldehyde is the silver mirror precipitate of silver solid being formed, and with a ketone we get no change. And then if we warm it with Felling's solution instead, our aldehyde gives us a brick red precipitate. I should have really said there blue solution changes to give a brick red precipitate, so you could add that to yours. And then with the ketone we get no change again. Okay, next up we've got to write 2 half equations for each method. Okay, so for the Tollens reagent, we've got silver plus aqueous ions plus an electron goes to give silver solid, and for the Felling's solution, we've got copper 2 plus blue ions there, plus an electron goes to form copper 1 ions in the form of copper 2 oxide, and that's our solid brick red precipitate there. Definition of an oxidizing agent, you could have checked the video for this. So, oxidizes or removes electrons from another substance by itself being reduced, gaining electrons. Okay. Next up, naming the test for carboxylic acids and giving that result. Okay, so the test for carboxylic acids, or any acid for that matter, is adding aqueous sodium carbonate solution. You get effervescence of carbon dioxide gas. If you bubble that through lime water, it will change from colourless to cloudy. Cool. Okay, next one then, we're going to look at identifying alkenes. You should really remember this from GCSE. So, first things first, alkenes contain these CC double bonds. That makes them unsaturated compounds. If you contain a CC double bond, then you are unsaturated, because each carbon doesn't have the maximum number of bonds that it could have. Carbon can form 4 bonds, and although technically it has formed 4 bonds, it's not formed 4 single bonds, it's formed 2 single bonds and 1 double bond there. Okay, so it's unsaturated via that CC double bond there. Okay, so we can test for CC double bonds or unsaturation or alkenes using bromine water, and if bromine water detects a CC double bond, it's going to change from orange to colourless. If I made that colourless, it wouldn't have worked. You wouldn't see it. Okay, right, so here's a visual example of the bromine water test. You can see that the alkene is floating. That's usually because organic substances like alkenes have lower density than the water that the bromine is dissolved in bromine water, so they float on top. And for that reason, the alkene doesn't actually mix very well with the bromine water when you first pour it in. So we've got to describe a method for how we're going to use bromine water. So the first thing we're going to do is transfer about 2 centimetres cubed of bromine water to a test tube using a pipette. That's the bromine water in the test tube there. Then we're going to use a pipette as well to put the suspected unsaturated compound into the pipette. Remember, it'll float on top to begin with because of its lower density. Then we're going to bung it up on the top, put our thumb over the bung and shake it. Okay, put your thumb over the top, because where organic substances are quite volatile, when you shake them, they evaporate very easily, and the bung can fire out the top and cover you in bromine water and that alkene, which isn't very nice, because both of those can be a little bit toxic. Okay, or respiratory irritants. And then, if it changes from orange to colourless, you know that your compound had a CC double bond. It's unsaturated. Whereas if it stays orange, then you're looking at something that's saturated, or in other words, contains only CC single bonds. Okay, so let's have a look at why this test actually works. I have taught this to you before. Okay, so because our CC double bonds are an area of high electron density, they're able to undergo electrophilic addition reactions with electrophiles. And bromine, Br2, is an electrophile, along with other things like sulfuric acid, lovely electrophile, H+, brilliant electrophile, and you've got things like hydrogen halides, so HBr, HCl, okay? You've also got other halogens like Cl2, I2. Okay, so electrophiles there, diatomic halogens, hydrogen halides and acids, all electrophiles that the CC double bond can attack, okay, under electrophilic addition. So let's have a look at this mechanism then. So if we start with this propene here, and we've got the bromine molecule Br2, well, remember that diatomic halogen molecules, there could be an instantaneous dipole occur in the molecule. So we're not talking about a permanent dipole like we have in hydrogen halides. We're talking about an instantaneous dipole. So it might be that one of these bromines becomes temporarily delta positive whilst the other becomes delta negative. So we call that an instantaneous dipole due to a sudden shift in electron density within the molecule. Well, this alkene in its area of high electron density goes, oh look, a delta positive bromine atom there. This is an electrophile. I'm going to attack it. So the area of high electron density, the double bond, attacks the bromine like this, from the middle of the double bond to the bromine atom. But that's making a bond with the bromine there, but bromine can't form two bonds, it can only form one bond, so we've got to show that bond breaking with both of those electrons going onto bromine there. Okay. Now we've got to make sure now we draw the correct intermediate. The question is do I open the double bond so I stick the bromine here on this carbon, forming a carbocation here, or do I open it this way, putting the bromine here, forming a carbocation here? Well, if I formed a carbocation on the end here, it would be primary, which wouldn't be very stable due to the positive inductive effect not being very strong in primary carbocations. Whereas if I form my carbocation here, then I would have a secondary carbocation, which is more stable. Okay, so you can see here this carbon is bonded to two others, so this is a more stable carbocation. Okay, so this is the correct intermediate. So now this bromine that had the electrons put onto it can now act as a nucleophile. Okay, so this is going to attack this this fully positive carbon. Okay, and form a bond with it, and then you're going to get the product there. Okay. So we can see now we've got a 1,2-dibromopropane as our product there. So essentially what's happening when you add bromine water, well, you're adding Br2. So it's going to undergo electrophilic addition with the bromine, and it's going to break the bromine-bromine bond, which gets rid of that orange colour. So it goes from orange, bromine-bromine bond, to colourless because there's no longer a bromine-bromine bond present. Okay, so task 4. I need you to name the test and result for unsaturated compounds, in other words, CC double bonds or alkenes. Then I want you to name an outline, that means name the mechanism and draw the mechanism for the reaction of 2-methylpropene with bromine water and name the product, and justify the intermediate you have drawn. Okay, so if you could pause the video here, complete this task on your Google Doc, then come back to it and have a look at the work through. Remember to use ChemDraw to upload your mechanism. It might take you a while to get used to the mechanisms. You can just use D's as deltas. Okay, but yeah, pause that video, upload your answers, then come back. Okay, right then. So the test for unsaturated compounds is you should have got bromine water, and it changes from orange to colourless. All right. Now our mechanism. So let's have a look. Our name of our mechanism is electrophilic addition. We're now going to outline that mechanism. Okay. So here is 2-methylpropene. So 1, 2, 3, 2-methyl. There's the 2-methyl. 1, 2, 3. There's the prop. Okay. And we haven't numbered the ene here because there's only one possible position for the alkene in propane. Attacking here the bromine atom from the middle of the double bond, okay, right from the middle to the bromine that's delta positive. Electrons, a lot of people forget this arrow, check to see if you forgot it. We've got to break the bromine-bromine bond onto the delta negative bromine atom. This is your more stable intermediate. You could have put the carbocation on the end here, but by putting the carbocation on here, you've got a tertiary carbocation, which is more stable than the alternative primary carbocation, other than putting it on the end here. Okay, and this is because the tertiary carbocation has the positive inductive effect of 3 neighbouring alkyl groups, which makes it much more stable. Okay, 1 alkyl group, 2 alkyl groups, 3 alkyl groups, much more stable. If you were primary, you'd only have this 1 alkyl group feeding in its electron density via the positive inductive effect. There's our product. Okay, and it's 1,2-dibromo-2-methylpropane as your product there. Now you would have got the same product if you went through the other carbocation, because the bromines are simply adding across the position of the double bond, except this is the correct intermediate that it goes through because it's the more stable intermediate. Okay, right, to finish this off then, you've got a second task which reviews all of the questions that I've showed you in exam format. So if you could find this document, Testing for Functional Groups Review Questions, and then upload your answers by Thursday's lesson. Thanks very much for watching, guys. I hope you like the format. If you've got any comments you want to make about the format, please do post below. I know I'm speaking very quickly, but I'm filming lots of these each day to get them out to all my classes. So if you could add any comments about any feedback about ways to improve it or the way we're uploading our work, that would be greatly appreciated. Otherwise, see you on Thursday for another video. Thanks very much, guys.